Let us start the afternoon session. The first speaker is Professor Liu from University of Strasbourg. And title of his talk is Twisted Hodge Groups of Hilbert Schemes of Points on Surfaces. So please.
Thank you. Thanks for the introduction, and I want to thank the organizers for the invitation. It's my first time in Taiwan. I enjoyed it very much. I want to come back again in the future. Okay. So I'm going to talk about something about the Hilbert schemes of points. It's a fairly classical object. So let me start with the definition of Hilbert scheme of points. So let S be let's start with a smooth projective surface. Okay? Then for some natural number, we can define the Hilbert scheme of endpoints, sometimes denoted by S bracket n. So it's the Hilbert scheme of subschemes of length n on S. So by a theorem of Fugate, this is a smooth projective variety of dimension 2n, and it admits a natural map. So whenever you get length n subscheme, you can look at its support with multiplicity. And this is called the Hilbert-Chow morphism, and this is a Crepin resolution of these varieties with quotient singularities. So it's a classical object. There is this principle saying that, okay, invariants of the Hilbert scheme can often be expressed as the same type of invariants of the surface itself. So I will put my results in this context, and so I start with listing some known beautiful results in this direction. Okay, so some results, some beautiful results. Known results to put in the context. So I will start with the most classical one by Hodge. Hodge, yes, on Betti numbers. Oh, by the way, the results are often cleaner, at least the formula is cleaner, if I put all the Hilbert scheme at the same time. So I will do that, and it's not difficult to extract the information for an individual Hilbert scheme from that formula. Okay, for example, for the Betti numbers, if I put all n together, if I put all the Betti numbers, x and t are just the formal variables, then this can be expressed as a product of the 1 minus, I think it's bi, no, yes, bxi plus 2k minus 2, t to the k to the power of minus 1 to the I, that's right, and the bi of s. In any case, the Betti numbers of the Hilbert of the surface determines the Betti number of the Hilbert schemes. Okay, so the second example is this direction is for cohomology or Hodge structure. This is due to Hodge again with Zorg. Okay, and the formula looks like this. So if I take, now this is an isomorphism, maybe I need more space. This is a nice isomorphism. I have some problem with the chalks. Isomorphism of multi-graded vector space. So I take, say, no, sorry, the cohomology of the Hilbert scheme, say with rational coefficient. So this is the Hodge structure, graded Hodge structure. I twist it by n and shift by 2n. So I get the middle cohomology to weight 0 and the degree 0, and I take t to the n, t is just a formal variable, then this is a multi-graded vector space, will be isomorphic to the total symmetric power of the following direct sum formed by the cohomology of the as a Hodge structure of the surface itself. So I put like T to the K here, okay? So here, let me say that total symmetric power is in the super sense with respect to this cohomological grading, but with is the usual sense for this grading with respect to the power of T. Yes. Yes, yes, yes. So you can basically forget it. So this is an isomorphism of graded pure Hodge structures. So if you don't do this, then it's just ungraded. Yeah, basically just two ends to make degree middle cohomology to the degree 0, and n is the theta twist to put into weight 0. So it's now it's isomorphism of graded pure Hodge structures. Yeah. It doesn't really matter. Okay, right. Now the third example in this direction is the immediate consequence of the second. Let me maybe number them. It's number 1, it's number 2. So number 3, Hodge numbers. Okay, again, of course, due to Goethe and Sorge, there's no difficulty in extracting the Hodge numbers. N is equal to 0, and you take P, Q, so it's H, P, Q. The Hodge number of the Hilbert scheme, if I put X, Y for the formal variable, yes, that's what I said. So this total. Yes, yes. So this total sim is a super sense with respect to this cohomological degree, but in the usual sense with respect to the degree of the power of T. Yes. Yeah. So you can extract this Hodge number. So this, again, this is the usual trick of exponential things. PQ from 0 to 2 this time. So 1 minus 1 minus the total degree that is the super times P. So there is this shift because I'm putting all the shiftings on the right-hand side. Otherwise, you just do the change of variable of T over XY, something like that. So it's minus 1 to the minus to the minus 1 P plus Q of H P Q of S. I think that's the formula. Okay, so you can extract the PQ Hodge numbers. And of course, you can further specializing. For example, you can take Y to be minus 1. Then on the right-hand side, you just get some, on the left-hand side, you just get some Euler characteristic of certain cohomology. This is called the Chi-Y genus. Yes, 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 of course. It's just the generating series of this identity. And yeah, it's 3 implies. 4 by specializing y equals to minus 1 and renaming x to minus y, actually, because it's nicer to put minus 1 here. So s bracket n, t to the n, and 0. So this is the exponential. So I rewrite everything on the right-hand side, and it's not very difficult to find the following formula. That is, for example, in the book of Goethe, lecture notes on Hilbert schemes. Okay, so Chi-Y genus of the Hilbert schemes are determined by the Chi-Y genus of the surface. Okay, let's continue. Number 5. So this is called the Hodge homology. So the Hodge homology satisfies a similar thing. I'm just showing you some patterns, and probably in the end you will appreciate the beauty of all these formulas. So again, it's the total sum, total symmetric power of the Hodge homology. Oh, sorry, Hodge homology. That's the point. Yes, of T to the K. Again, this is not new. I mean, it's not difficult because it's also a consequence of 2 by the so-called Hochschild-Koster-Rosenberg isomorphism, because on the right-hand side, on both sides, the Hodge homology is just a direct sum of Hodge groups. And you play with that, you obtain this same result on the blackboard. So you just use 3 and the equation 2. And one can further generalize that, and this is a recent theorem that I obtained in the collaboration with Peter Bellmans and Andreas Krug. So the cohomology group is actually not new, but there is no name, so we call it the Hodge-Serre cohomology. Cohomology. So this is a theorem. This is a formula that we obtained with Bellmans, myself, and Krug this year, maybe last year, I forget. So yes, so it's the formula. So I didn't define what is Hodge-Serre cohomology, but let me just recall you very quickly. So whenever you have a smooth projective variety, this is just the hypercohomology of the R home of the delta push forward of omega x shifted by the dimension of x to the power of k. If you want, this is the the extension groups of the identity functor with respect to the kth power of the Serre functor. Anyway, it's just some coherent cohomology that one can define. So this is a definition. And the formula for Hodge-Serre cohomology is the following. So for any fixed integer k, not necessarily positive, just an integer k, the Hodge-Serre cohomology is a graded vector space. And if I put all the Hilbert scheme together, I get an isomorphism of total symmetric power. This time there is a little bit of caveat, HS, Hodge-Serre cohomology of S, but with the degree with I, so let me call it I, plus K minus 1, 1 plus K minus 1 times I, T to the I, okay? So I didn't say, but the zero grade Hodge-Serre cohomology, just a Hodge cohomology, and the HS1 star of the Hodge-Serre cohomology, just the Hodge homology. So Hodge-Serre cohomology extending Hodge homology and cohomology to all the powers of Serre functors. And actually, if you put the Hodge-Serre cohomology together, then you get a formula for the Hilbert scheme. Okay? So this is also a pattern in this direction. And of course, there are some other few invariants one can talk about, which is not the main point of the talk, but let me give it nevertheless. So Goethe showed that in the Grothendieck group of varieties, so you have this, the motif, the virtual motif of the Hilbert scheme, I guess normalized to the n, is just again total symmetric power. I mean, this is a well-defined operation in the K0 of variety suitably localized. Infinity, yes, the virtual motif of of S, sorry, T to the K. Okay, so this is the in the Grothendieck group of varieties. Maybe you can localize. This is not really necessary because if you fix an n when you develop everything, the denominator, the power of denominator on the left-hand side will be greater than the right-hand side, so you can eliminate. And in a more stronger, I cannot say stronger, but in an analogous form, we have the result of the Gaddardo, Miolini. Yes, on Chow motives. So the motive of the Hilbert scheme suitably take the twist. If you want to mix the motive, then you just also do the shift 2n, but I will not do it here. So let me stay in the category of pure motifs, then this is also isomorphic to the total symmetric power of the sum of the motif of a surface twisted to the k. K is at least 1. Yeah. And of course, if you want, there is also a famous relation between their derived categories. This is Bridgeland, King, Reid. Maybe you should also put the result of Heyman to get the following thing. So the derived category of the Hilbert scheme of endpoints in the coherent is equivalent to the symmetric n to the derived category of coherent sheaves. So this symmetric power is in the sense of DG categories. Yeah, so yeah, I can also go on, but let me stop here for the very beautiful list of results between Hilbert schemes and the surface itself. Okay, now if I put a little bit more data, I can actually refine certain results here. Now instead of having just a surface, I can have a line bundles on it. Let L be a holomorphic, always holomorphic. Line bundle. Yes? Well, if you take the glutonic group of the K0 on both sides, then you recover the rationalization of the Chow group. Then you use Mani identity. Yeah. So, but this is an integral thing. It's a category. Yeah, but they are of the same nature, motivic nature. Yes. Okay. Now let L be a line bundle, holomorphic line bundle on S. I can associate a natural line bundle on the Hilbert scheme. So how can I do that? Well, on S to the power of n, I have the line bundle, how to say, L box n. It's just the tensor product of all the line bundles on each vector. I put them together, I call it L box n. Let me call it var pi. So this line bundle has a natural action of Sn. Then I get a natural line bundle on the singular quotient space, which is I just take the push forward, the push forward of this line bundle and take the invariance. Okay, this is a line bundle on the singular space, and its pullback is actually this line bundle. It's just the descent of that. Line bundle, now using the Hilbert-Chow morphism on this, I can define Ln. This is a line bundle that can play an important role in this talk, is defined as the pullback of this line bundle, okay? So this is a natural line bundle on the Hilbert scheme. Now I can ask whether certain invariance of the pair, the Hilbert scheme together with this line bundle is determined by the pair of SL. Okay, now I can continue maybe 1, 2, 3, 9, 10, right? 1, 2, 9, 10, yes. So I can continue. Let me start with Gotcha all the time. No, this is a rank. This is. Yes, but they are still different. So there is this total exceptional divisor. Yes, yes. So Claire said that there is a tautological tautological vector bundle on the Hilbert scheme, which is rank n, which is the direct sum of all the points, all the lines on the support. If you take the determinant of that, it will be the tensor product of this line bundle together with the line bundle determined by the exceptional divisor of the Hilbert-Chow morphism. Or the inverse of it, I cannot remember that. But yeah, they are related. Okay, so but I will only consider this line bundle. And Gotcha, yes, prove that it's called a refined chi-y genus formula. So it's a generalization of number 4, yes. So always chi minus y to the Hilbert scheme. Now we put Ly, so I didn't define what is the chi-y genus of a variety with a line bundle, but this is not very difficult. It's just the chi of x. Let me do this. P, omega p of x tensor this L, and I put y to the p. Okay, that's the definition of the refined chi-y genus with value in even some vector bundle, but I will only talk about line bundle here. And the formula also generalized in this direction. So it's p to 0. I cannot remember it by heart. Let me just copy it. Tk minus 1 p to the chi of s of omega p of s tensor L to the k. Okay? So this is not the formula you will find in Goetsche's paper. So he used, because this is some genus invariant, so he used the Riemann-Roch formula in the end. So on the right-hand side, it looks completely different. But in my paper with Andreas and Peter, we reformulated everything in this form. So they are equivalent. So there's no Riemann-Roch going on here. And if you want really to write the right-hand side in terms of some chi-y genus, you can also do that. Let me provide you the formula just for completeness. Is at least 1. The formula will be a little bit more difficult, more complicated, but nevertheless, it's in terms of the chi-y genus. Why not erase this line? So now here is the chi-y genus of S. The point is that there is L to the K, okay? So this is Goetsche's formula. Goetsche's refined chi-y genus. And I can also generalize the formulas that we obtained with, we also generalize the formula here, 5 and 6, into the formula of so-called Hodge homology with coefficients. Okay. So this is again in the same paper with Peter and Andreas. So the formula looks like follows. N to the N. So the Hodge homology with coefficients is either I think so. It's not in the, yeah, I think so. You mean by genus argument? Chen class. It's not how he, I think it's not how he proved, but I think so. So there is some theory of Y.P. Lee and Rahul Pandey of the cobordism of pairs. I think, I didn't check in detail, but I think in their cobordism array of pairs, this pair is determined, the cobordism class of this pair is determined by the cobordism class of the pair SL. And that says that you can somehow, find some generators and check both sides on these, only on these generators. But I didn't check, but I think so, it's plausible. Yeah. Okay, so let me write down this formula. K is at least 1, sorry. Hodge homology with coefficients, L to the K. No, it's the line bundle, sorry. Yes, I didn't state the strongest result of Goetche in his paper. He actually determined all the elliptic genus of this pair, which, of course, when you specialize the variables, you get this chi-y genus. So this is not the strongest form, but this is a form that I'm able to refine. So that's why I stated here. It's just one of the corollary in his paper. Okay? Okay, so I wouldn't define what is the Hodge homology with coefficients, but more or less something like this. Okay, with some shift of degree. Okay, So this 11 implies 5 and 6. It's a generalization of 5 and 6. 10 is the generalization of 10 is generalization of 4. Okay. So I wrote on so many blackboards so many beautiful results. So the humble goal of today is just to add some new contributions in this direction. So as you can see, this Hodge homology by the Hodge-Kostner-Rosenberg isomorphism, it's also a direct sum of something called twisted Hodge groups. Also, this chi-Y genus by definition is also alternating sum of twisted Hodge groups. So the goal is to find a common refinement of 10 and 11, hence many other results on the left, by computing all the twisted Hodge groups. So let me define what is the twisted Hodge groups. Okay, so let me be the general smooth, maybe just a compact complex manifold, and L some holomorphic line bundle on X. Then I will define HPQ of XL to be the HQ, the usual formula. Omega XP, the bundle of P forms, times L. And its dimension is called the PQ twisted Hodge number. Okay, so this is what I mean by a twisted Hodge group and a twisted Hodge numbers. And also, I will need a little bit of extension of this definition is that if X is not smooth, but only with quotient singularity, so if X with quotient singularity, if X with quotient singularity, then I just put some bracket here to say this is the reflexive differentials. Okay? So for orbifolds, omega bracket P for orbifolds is by definition the J lower star of omega regular P. Okay? So where X regular is the smooth part, open immersion. So if X has, so this is also the same thing as just the Kähler differential, then you take the double dual. Okay. So this is the definition of twisted Hodge group. Then the main result of today is the computation of the twisted Hodge group in this setting. Okay, so the theorem A, let's say. So S as before, so S is a complex surface, not necessarily Kähler or projective, and L some line bundle on S, and we can therefore define a line bundle on the Hilbert scheme. Okay, I won't rewrite the definition. Yes, so we have isomorphism of graded vector space, just as before. So HPQ of this vector space, Q T to the N, is isomorphic to the total symmetric power of the direct sum PQ of the HPQ of S L to the K. With a shift, sorry. X P plus K minus 1, Y to the Q plus K minus 1, T to the K. So this is the formula. So I can also remove the X, Y variables just to be more succinct. This can be written something like some bi-graded vector space. Okay, this really means you sum up all the degrees. And this is a symmetric power of the bigraded vector space of SL to the K. Shifted for the bi degree, y minus k, and put the t to the k. Okay, this is just another way of writing the first formula. So this really means that you put HPQ to the degree p plus k minus 1, q plus k minus 1, some shift. And we have an isomorphism of trigraded vector space. Again, the total symmetric is in the super sense with respect to the sum of the degree, and in the usual sense for the k. Yes, yes. 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 Yes, this is what I'm going to do. Yes.
So, yes, my question was maybe more generally, you did the formula simply to describe the R2.
That's what I'm going to do? Yes. Yes. This is what I'm going to do. Yes. Yes. But there is maybe a hidden question is that maybe whether I can replace a line boundary by some vector boundary, because I can pull back. But that doesn't work, because in the definition of the Ln, if I do this to a vector bundle, it's not a reflexive sheaf. Sorry. It's not a locally free, it's only reflexive. So it's just, why we care about reflexive. Yeah. So I stay with, and it's pullback. If you take a double, anyway, it doesn't really make sense. One can do that. It doesn't really matter.
You just said compact surface.
Yes. No. Compact complex compact complex manifold of dimension 2. Yeah, this is for later use. It's, sorry. Yeah, sorry for the confusion. And it's a corollary, but let me say it in as a theorem, is that I can take the dimension, so I get the generating series. Generating series, PQ, and I get the generating series for twisted Hodge numbers. XP, YQ, T to the N is equal to the product 0 to 2, 1 minus graded degree, xp plus k minus 1, yq plus k minus 1t to the k to the minus of degree, hpq, sl to the tensor of k. Okay, so this is the dimension. So the twisted Hodge numbers of powers of k determine completely the twisted Hodge numbers of ln for all Hilbert scheme. So this is actually, there was a conjecture by Boissier where he didn't put this k. So naturally, there are some counterexample produced. And then in the previous paper with Peter Bellmans and Andreas Krug, we guessed this formula, and we formulated this conjecture. And today is just to prove this formula. Okay? So the way we guessed it is not by the method that I'm going to explain today, but rather by our results there. We proved 11 using non-commutative methods, because Hilbert scheme is derived equivalent to the quotient stack by the symmetric group. And we can compute that the Hodge homology of the quotient stack. So we get this formula and its dimension. That helps us to guess this formula. But today, I'm going to prove this formula in a completely different way.
Is the categorical meaning for these twisted Hodge numbers?
Categorical meaning, I mean, it's the group between two things, but, oh yes, maybe, so I didn't succeed, but at some point I want, so this is the dimension of X group between O and some R pi lower star. Yeah? So it will be helpful to compute the Bridgeland-King-Reid image of the omega p in the derived stack. I have some guess, but I didn't really succeed because there are some singular things bothering me. But yes, this is a direction that one can try. So we put everything to the equivalent category and compute the X group. I guess that's your question, right? Okay. Okay. Yeah, let me say, okay, so this formula, of course, if you take L to be the trivial bundle, that recovers something I already erased. It recovers number 3. So in all the literature that I can find, there is no such computation of Hodge numbers for non-Kähler surfaces. So I just cannot find it in the literature, but yesterday I discussed with Claire. She's convinced that using some methods by De Gattaro and Miolini, some correspondence, one can also nevertheless prove these 3 for non-Kähler surfaces. But anyway, this is the formula that I found, and I cannot find a formula in this generality of complex surfaces in the literature, non-Kähler ones. And if I take y to be minus 1, so just some remark, if you put y to the minus 1, that recovers the formula of Goethe. So it's indeed a refinement of Goethe's formula. And remark that 10 uses essentially like Chen numbers, Riemann-Roch formula, etc. But here to compute individual cohomology, you cannot use Riemann-Roch formula. So that's the difference. And also, if we put y to the inverse of x, that's going to recover my previous work with Peter Bellmans and Klug, so that's going to recover 11. Okay? And of course, these are recovering 1, 2, 3, 4, 5, 6, 7. No, 1, 2, 3, 4, 5, 6. Also. All these previous results, they are more or less contained in these 2 formulas. Okay? But this is not the main application that I'm interested in. The main application and the true motivation for me to do all these things is to study the deformation theory of the Hilbert scheme. Yeah, because you want to define. So which bundle you want to consider? This here is Ln. You want to take En. So
you have the universal. There is a vector bundle of the universal, which has the fiber.
If you take
universal correspondence.
Then you get something called a universal bundle, whose notation is probably E bracket n. But this is a vector bundle of very big rank. It's more or less the direct sum of fibers, but here I'm looking at the tensor product of fibers. Other questions? I was erasing this. The true motivation is for deformation theory of Hilbert scheme. So Hilbert scheme is a classical object. Its deformation theory is very important. If you do some hyperkähler geometry, of course, this is the main source of hyperkähler varieties as deformation of Hilbert scheme of K3 surfaces. So this kind of thing has already been studied a long time ago. So deformation theory application. The main application is deformation theory. Theory of the Hilbert scheme. And actually the results works for duality space of compact complex surfaces. So it's a deformation of a complex structure on this complex manifold. So let me recall some previous results. So Fantecchi proved that if S smooth projective with either let me just write the groups, H0 of the tangent to be 0 or H1 of the structure sheaf to be 0 and H0 of the anti-canonical to be 0. So if all these conditions are verified, for example, if S is a general type surface, then there's no such vector fields and no anti-canonical. So then the deformation, the local Courant-Nishi space of S naturally goes to the deformation space of S bracket n is an isomorphism. That's a theorem of Fantecchi. And also, there is a theorem of Hitchin saying that if S is smooth projective with H0 of omega S to be 0, then we have a splitting Schrödinger sequence. Let me just write. It's a non-canonically isomorphic way. So the tangent space of H of the tangent space of deformation space is isomorphic to the tangent space of deformation space plus the sorry. This is the condition is wrong. H of OS. Sorry. Then there is this anti-canonical, of course, K3 surface. Okay? So these are the previous results that we know. But now today the application that you call theorem C. Local result. I don't understand what the local result. Yes, this is a Courant-Nishi space. Formal, yes, this is a formal, yes. It's a Courant-Nishi space. It's the germ of analytic space, yes. So the result that I'm going to present is that for very general S is just a compact, complex surface, so smooth surface, or complex manifold of dimension 2, compact, complex, smooth surface, okay, dimension 2. Yes, then HQ, for any q, integer HQ of the Hilbert scheme with value in the tangent. Of course, these are the important cohomology groups for the deformation theory, can be completely computed. So let me write down the formula. The tangent of the Sn plus, there are three factors, as q minus 1 of the n minus 2 to the O, tensor H0 of the anti-canonical plus q minus 2 of the same thing, tensor H1, same thing. Yes? Sorry, you what? Oh. This condition is not satisfied for K3 surfaces. That's right, K3 surface is here. Yeah, but the K3 surface is not, it was known way before. Sorry for the chokes. Tensor H2 of, okay, so this is the total description of all the cohomology groups that is involved in the deformation theory. So in particular, let me write down the three most important deformation groups, 0, 1, 2. But I have to assume S to be connected. And N is at least 2. Okay, I guess it's harmless. So H0 of the Hilbert scheme of the with value in the tangent is isomorphic to the same thing for the surface. This is not new, by the way. H1, if Q equals to 1, then this has three terms. So the deformation of the Hilbert scheme, there is of course the deformation of the surface along with it. Then you have this term H0 of S, T. I invite you to look at the formula of Fantecchi. Now, it's plus H0 of S of omega S dual, okay? So she said the deformation theory is isomorphic. If one of these two is vanishing and this is vanishing, then of course the H1 are the same. So this recovers at least at the tangent level the theorem of Fantecchi. Then for the obstruction space, it's a little bit longer. there are many terms. So h1 of the tangent, let me not write s. h1 of tangent tensor h1 of O plus h0 of the tangent tensor h2 of O plus h0 of the tangent tensor wedge 2 of the h1 of O. It's not finished. Plus h1 of O tensor h0 of bitangent, meaning anti-canonical. And the last term, h1 of the anti-canonical, which is the bitangent, of course. Okay, so this is the complete formula for h2. And also, I claim that the...
I'm sorry, do you say that this formula was a particular case of...
Yes. You can compute that. I didn't, but if you believe me, you put q equals to 1 and you get this formula.
For instance, the second summand,
Then it goes away, of course, q minus, h minus 1 is 0.
there is no
There's t, t's here. Yes, all the t's coming from here. So the tangent of a product is the sum of the tangent. You develop each term by the Queen's formula, you get hi of the tangent tensor hi of O, then you symmetrize. It's the rank 2n. Yeah, anyway, if you believe me, it's the result. And I claim that the Polish 9-house bracket, which goes from H1 to H2, which controls the obstruction. The obstruction map is given by the 9-house bracket in the most natural way. For example, if I have an element, say here, then the bracket is bitangent, so it goes to tritangent. There is always a degree shifted by 1 in the tangent factor. So this always go away. For example, if you have one element here and one element here, then their brackets will go to this term, etc., by the most natural way. So I would say this theorem completely determines the formal deformation theory of the Hilbert scheme, because you have the H1, you have the tangent space, you have the obstruction space, and you have the nine-house bracket. Okay. Yes. I didn't prove the theorem, but I forgot to say theorem 3 is a consequence of theorem A, because simply HQ of a variety of the tangent is just HQ of, I don't know, omega dimension minus Q tensor anti-canonical, right? So it's a Hodge number with a value. That's why twisted is important. This is a dual, yes. This is a dual, anti-canonical. Yes, D minus 1, sorry. Yes, thank you. Yes, so it's a particular case of twisted Hodge group. And they are all there. So this completely determines the deformation theory, and I invite you to recover these two theorems of.
So if S is a product of two curves, do you recover this whole theorem of Kempf about the deformation of the
I didn't know that. Maybe I can add it into the next version of the paper. I'm sure it will recover. I mean, it's complete information. It can, either I'm wrong or, yeah. Thank you. So it's by Kempf. Yeah, thank you. I'll check out. Yes. No. This is particular. This doesn't have anything to do with deformation theory. No. So how to recover Hitchin? Hitchin says that if this group is 0, then this group go away. So they are isomorphic, right? No, he didn't say that. I think it's not automatic. No, so an element here is a sum of one. It has a component here and a component here. When you take the Nyren-House bracket, so let's call it alpha and beta, and then beta bracket beta is obviously 0 because there is no wedges 3 of the tangent. But alpha bracket beta, the crossing terms, it will land in H1 of the bitangent. It's here. It's not necessarily 0. So it can be obstructed.
How about this, just H0 part, H0s and omega s dual? I mean, the second component
Yeah.
The second component
Is Hitchens, I mean, it generalized Hitchens result. This can be non-zero.
the question is about obstructed. In the Hitchin case, if S is unobstructed, is S also unobstructed?
In the Hitchen case, no, I don't think so, because just I explained that there is a non-trivial bracket here to be checked. Yeah, it's not, it's lands here, but of course, if there is no H, if there's no group, it's unobstructed. Okay, so this, by the way, the middle term there, nu, can be non-trivial, for example, for a bi-elliptic surface. So it's a genuine group that can really appear. Okay, now in the next 10 minutes, let me prove theorem A. Are there more questions? So proof of theorem A. Theorem B and C are just the consequences of theorem A. So in the old paper with Bellmans and Krug, we use non-competitive methods, derive the categories, Bridge and King rate, etc. But in this result theorem A, I didn't use this derived thing, just a classical Hodge theory. So it's classical Hodge theory. But somehow in a modern form, it's the relative Hodge theory of the Hilbert-Chow morphism of pi. Why is it? So when I say relative Hodge theory, it's about the Hodge module that produces here when you push forward things, okay? So, maybe I don't have time to recall what is a Hodge module. Basically, it's a generalization or variation of a Hodge structure. You replace the flat connection by some D module, and you replace the local system by the perverse sheaf, so that they are related by the Riemann-Hilbert correspondence, and then, and with some subtle conditions developed by Morihiko Saito. So how can I start? So the most important observation, which is also used by many authors, is that pi is semi-small. So this is the starting point. Pi is semi-small really means that the dimension, let me just denote this by x and denote this by y. So x times x, y is dimension x, okay? Dimension 2n, right? Okay? And once we know semi-smallness, the decomposition theorem is particularly nice, but we have to first stratify this pi. So stratification of pi, okay? So first of all, y lambda, so this stratification is enumerated by partitions of n, okay? So y lambda, which is Sn lambda, is by definition points of the shape lambda. So it's something like, I don't know, x1, so if I write lambda as lambda 1, lambda L, then it's just XL with XI distinct, right? So this is the smooth, locally closed stratum of the base. And also, if I restrict pi to the pre-image of y lambda, I get x lambda. Yeah, let me just call it x lambda, goes to y lambda. Then what is the fiber? Fiber are scheme structures on this kind of cycles. So this is actually a fiber bundle. A fiber bundle with fiber, let me call it F lambda. Fiber is the scheme structures on these fat points. So it's actually the product of the so-called Briançon variety. Briançon variety is just a Hilbert scheme of subschemes that are supported on one point. So these are the product of Briançon variety. They are irreducible by theorem Briançon, and its dimension is lambda 1 minus 1, etc. So the dimension of f lambda is n minus lambda, which is exactly the half of codimension of y lambda, if you compute it. Therefore, all strata are relevant. All strata are relevant. Okay? Now we can use a particularly nice form of decomposition theorem due to Borel and McPherson. So general decomposition theorem is due to Beilinson-Bernstein, Deligne, Gaba. But in general, it is very difficult to determine the supports. But in a semi-small case, there is a theorem of Borel-McPherson. It says that, okay, if I push forward of the shifted structure sheaf, constant sheaf, is isomorphic to all the direct sum of all the relevant strata that is indexed by L and IC complex of Y lambda bar with trivial local system. Okay, so this is Borel-McPherson. But then if you put the Saito on it, then you can upgrade this isomorphism of perverse sheaves into an isomorphism of Hodge modules. So you just put an H here, and you just write IC. Okay, that's easy. You just write this is the Hodge module, constant Hodge module on X. When you push forward, you get a Hodge module, pure Hodge module, and this is direct sum of Hodge modules. Okay. Now you just take. Then it's very easy to see that Y lambda bar has a natural normalization. I didn't write. So lambda, if I write like A1 times 1, A2 times 2, etc. to AR times R, then it has a very natural normalization to the AR, and it goes into N, yeah? And let me call this map nu lambda. Then because nu lambda is basically birational to its image, proper finite, this Hodge module isomorphism becomes to this nu lambda push forward of this IC Hodge module of this product. And now if you talk about Hodge module, the weight somehow becomes important. So you get the variation of a Hodge structure of weight 2n minus the length of lambda. Anyway, there is some shift of weight which will shift the filtration. Now in the last 5 minutes, I can conclude quickly. So if I have an isomorphism Hodge module, which looks like a topological thing, but the power of Hodge module is that there is underlying D module. So you take a D module, underlying D module isomorphism of this Hodge module. A Hodge module has 3 components: perverse sheaf, D module, and a filtration on it. So you take the filtered D module, you get something you get the pi. So for D module push forward, it's denoted like this, and the underlying D module of the constant Hodge module is the canonical bundle. That's just convention. And with the canonical filtration that I don't have time to explain, it's really easy. It's just, it has only one graded piece at degree minus 2n. And then you get isomorphism of exactly the same thing. So nu lambda push forward of the D module that I denoted by the same formula. And you can see actually they are just a box tensor of all these D modules, okay, with filtration. Okay, the filtration is very important, and it's shifted by the variation of Hodge structure. So it's minus lambda plus n. Okay, Tate twist will just shift the Hodge filtration. It's just like a variation of Hodge structure. So you get an isomorphism of filtered D module. Okay, now there is the key point. The key point is to apply a very interesting functor to it. So you apply the functor of the drum complex together with the graded piece of minus p. Okay, this is one functor, although it looks like 2, but it's not actually only well defined when you compose them together to get some coherent sheaf on the base. So if you like this plus a theorem Saito of Saito strictness theorem, it says that basically the push forward can commute with a girder, okay? So let me commute them. So it's R pi push forward of girder applied to this. If you look at the definition, it's just the omega of P of X shifted by the 2n minus P, okay? So the point is that the omega is a vector bundle of very high rank, is actually the GER of the Durham complex of a very simple D module. So this is the isomorphism of direct sum of lambda of n. And yeah, apply the same strictness theorem here, so you get a new lambda push forward of all this graded Durham of all this stuff. But don't forget about the shift. So it's a point, let me just write. So I use the minus P, right? Minus P plus n minus lambda. Anyway, it's just some shifting. And then the gradient of the Durham complex of box tensor product can be open, and you get a very nice formula by Queen's form. So Queen's allows you to conclude the formula that Claire was asking. So this is isomorphic to the sum of n of, let me see, it's, anyway, it's some formula of p plus minus n of some IC, sorry, of some reflexive differentials of p k s of ak. Anyway, it's very easy to see with some shift. Okay. Once you have this formula, you just tensor with the line bundle on the singular variety and take the hypercohomology. With some elementary computation, you can conclude. That's the way to compute it. I think that's all for me. Thank you.
Thank you very much. Are there any questions or comments?
Yes?
So in the upper right corner, you said that u lambda was the normalization?
The factors rules normalization.
Factors?
Yes.
It's not birational.
Well, so I want to define new lambda actually. So this is birational. Yeah? Birational?
No. If you take S cross S to S2, it's not birational.
What do you mean by it is birational? It's how to say? Let me give you an example. If lambda is something like twice 3 and 1, huh? 1, 1? Ah.
Okay, you put the ones together. Okay.
Yes, that's the point. So A1 times 1. So each cycle here I repeat it once. Each cycle here repeated twice, etc. N and N is sigma of KAK. That's to be remembered. Yes. I think in this case, it's indeed the normalization.
So in the vector bundle case, the analog, you say that it's never locally free.
Yeah, it's not the locally free bundle on the base. So yeah, basically, what you can always do is you take this key formula, you take this formula, and you tensor something on the base and you pull back. It always gives you something computable. So the point is that there is no, so given a vector bundle on S, I don't have an interesting vector bundle that is pulled back from the base. That's the problem. So I don't have an interesting vector bundle here that is pi upper star of something constructed in the same way.
But the left-hand side of the theorem A does make sense for a vector bundle.
No, then what is Ln? I just don't know how to make sense of this Ln. Ln is pi, no, it's not pi. Let me call this, so this is pi. This is something I call the var pi. So it's var pi lower star of Sn of something. That's my definition. Of course, you can apply the same definition, but then if you pull back this vector bundle to the top, it's not a vector bundle. It's some reflexive sheaf. Yeah, pull back. Yes, but this is not a vector bundle. This isn't, huh? Right, so this is not, I don't know, it's not vector bundle, this is a reflexive sheaf.
I understand that's not the vector bundle. But you take the, you have a vector bundle on the base, and then you have a vector bundle on the here by using the,
Yes, then I don't know how to compute.
the left-hand side. So what is the answer?
Yes, this is tautological boundary, I mean at the point given subscheme.
So the left-hand side makes perfect sense.
You are right.
Bracket that.
Right, but that's not what I computed because ln, yeah, and I don't know, yeah, my question, yeah, it's just I don't know how to compute the cohomology twisted Hodge group of this vector bundle. And I don't know how to compute many things. I don't have time to go to the section of the open questions. So you can look at some natural line bundles like the divisor, exceptional divisor, and the vector bundle of this kind. Many things, elliptic genus. I cannot compute all of them. It's only the start. Yes.
Are there any other questions or comments? So thank you very much again.
Thank you.